Okay, good. Thank you for the introduction, and let's dive right in. I want to start on a very cheerful note, which is that we have a problem. And the name of the problem is supply chain attacks. So you may have read of examples like Log4Shell or SolarWinds or the xzutils fiasco. So let's talk about, let's see what these are about. So on your computer, you can use Chrome to browse the internet and download some files, which is all very good as long as Chrome does what you want. But Chrome uses third-party libraries. And an attacker could install a backdoor in a library used by Chrome. And in principle, they could gain the exact same access to your computer as Chrome. And if they did that, that would be really bad news, right? So they could steal secrets from your disk. They could read your passwords that you type, and they could do the very same thing to millions of other people. And ultimately, the problem is that it's enough to compromise just a single dependency, and modern applications can have even thousands of them, which happens for JS. An appropriate architecture makes applications much more resistant against such attacks. And we've known this for half a century. So paraphrasing, every part of a program should operate using the least authority necessary to complete the job, right? That's the POLA, that's the principle of least authority. Now, okay, it's just a principle. We also need a pragmatic enforcement mechanism. So one approach is to compartmentalize parts of the program, which is to say we run them in an environment such that accessing anything outside of this environment is completely controlled. So what Chrome does is it runs libraries inside the processes, which you may have seen. So this does the job, but it leaves a lot to be desired, right? Because now you need to communicate between processes. Now you need to express policies in OS-level concepts. And the only way to tell if your policy is too restrictive is to run the program and see if it crashes. So I don't think I need to convince you that things could be better if we did a PL-based approach. And it turns out we do have such an approach. So the object capability model is great here. It's very flexible, as we will see, and it's very natural for people familiar with OOP, which is a lot of people. But so far, it had a particular issue, which is that adopting it required migrating the entire application in a single go. And so what if that didn't need to be the case? What if we could take an existing application and gradually migrate it to using object capabilities, every part by itself? What if we could migrate the ecosystem library by library, and applications could use any library without having to compromise on enforcing security policies? So that's the vision that we have, and to help realize this vision, we developed the gradual compartmentalization approach, and as well as Gradient, which is a proposal for a Scala-free extension utilizing the approach. Okay, so now you know what's on sale. So let's motivate object capabilities. So the current status quo is that library code can access whatever system features it wants, right? So here we have some Scala code which uses the log4j Java library. And it might look innocuous, it might just look like it's just logging things, but actually it could be downloading some code from the internet and running it, right? Which is basically what the Log4Shell vulnerability actually was. And the situation would be a lot better if we were using object capabilities. So the basis of this model is that code starts with no ambient authority. So the access to all system features is only possible by calling methods on capabilities, special objects, and they need to be received from the outside. So what we see here is the same snippet as before, but now it's in Gradient, right? Our proposed Scala-free extension. We are using caplog, which is an object capability version of log4j. And now, to create a logger, we first need to instantiate caplog, right? So here, main initializes caplog with capabilities for accessing the file system, network, and evaluating code. Okay, so it's already better because that eval thing over there, that's quite fishy. Where do these guys come from? So this code is actually organized into modules. And basically, you can think of them as like they are classes. They are just templates for objects. They even have constructors. So the main method is in the special main module, which gets the capabilities it needs from the runtime. and then it can pass them to other modules like caplog. And ultimately, if you want to do anything of importance, you need to call methods on capabilities. So here is how this program starts. First, there are only some basic capabilities which we call devices, right? You need to use those to access the real world. And to actually start the program, the runtime needs to initialize the main module and then calls its main method. And so then code can instantiate modules like caplog. And the thing is that caplog wants to access system features, but it can only ask for capabilities, right? Politely. And it has to get them from the outside, right? So that is our compartmentalization mechanism right there. We can choose what caplog gets. And in the snippet we saw, main gave caplog direct access to device capabilities, which maybe wasn't so good. And if we want to restrict what caplog can do, we need to be a bit more subtle about it. Okay, so let's say that we are reasonable and we want caplog to only access log files and nothing else. So here is a schematic example of how to do that. First, instead of giving caplog direct access to the FS device, we use the restricted FS class to only let it access a single directory. And next, instead of giving it net or eval, we give it inert versions of these capabilities, which throw on every single method call. And the way restricted FS works is very simple. On every method call, we just check if it should be allowed. If not, we throw. If yes, we forward it, right? OK, so that's it. That's all we need. We just need to encapsulate some objects, right? So this is just standard object-oriented thinking, something that many, I wanted to say all software developers are very familiar with. And you know, the genius of object capabilities is that we are reusing this thinking to express security policies, which is exactly what makes them a very desirable approach for compartmentalization. But as I said, they do require a stop-the-world migration. So to secure an existing program with object capabilities, we need to migrate all the code in the program, including all the dependencies. And in extremum, this is very burdensome, right? So ideally, we prefer to migrate any part of the program independently of the others. So let's see how our approach promises to help with that. So fundamentally, we answer two questions. One is, how can classical code interact with code written with the object capability model? And two, what sort of access policies can we enforce when this interaction is going on? So what we want is that we want a coherent integration between packages of classical code and the object capability model, right? Now, such code can access system features, so we must act like it was a capability. There is no other way. So if a module wants a package like log4j, it needs to request it as a constructor argument, like we see. So, and for now, just ignores the hash. It means danger, and we will come back to that. So you should basically think of this as a funky import clause. Log4j doesn't have to be an object at runtime. We just treat it like it was. Next thing is that classical code accesses system features via system calls, but in object capabilities, that can only be done with devices. So to reconcile these two, we can just say that system calls are method calls to devices. So that's the picture that we should have in our heads. We act as though the log4j package was an object, and main had a reference to it, and log4j was doing its job by accessing devices, right? And we are interpreting existing code in this way, right? There is no modification to the package. OK, so far so good, but we still need to think about one last detail, which is how do we make sure that log4j doesn't access malware from the internet? And, well, we just need to put something over there. So before we could put our own objects there, but that doesn't work anymore. OK, so the idea is that we propose enclosed blocks during which only approved system calls can be performed, right? And using those, we can make sure log4j can only access the file system, right? We just always run log4j inside of an appropriate enclosed block, right? We say, within this block, only the FS device should be accessible. So that gets translated to a list of file system-related syscalls, and if log4j tries to access the network at runtime, it gets stopped with a runtime error, right? It's like a throw on a method call. So basically, the enclosed block allows dynamically creating compartments and running untrusted code in them. And we propose these blocks because they can be efficiently implemented with enclosures, which is a technique from, recent technique from 3 years ago. Okay, so there is a bit of a caveat here, which is that this thinking has to be extended to mutable objects because they can be used to indirectly access system features, but time is short, so details are in the paper. The core idea is that we treat all mutable objects as capabilities, and we only allocate them within certain memory regions. And in concert, these allow forbidding access to SOML or mutable state with enclosed blocks, and they integrate this with the object capability model. And we also have good grounds for saying that this can be applied to controlling access to secrets kept as immutable data. Okay, so here is the recap. We saw the enclosed blocks that we saw allow dynamically creating compartments for running any classical code that we might have. And the trade-off is that they work at a very coarse granularity. And because of the way we integrated classical code with the object capability model, enclosed blocks allow reusing existing OS-level concepts, like approaches, really, like enclosures, and they still permit expressing POLA policies with language-level concepts like devices. Okay. So that brings us to the last part of the talk, which ties these two systems together. So in gradual compartmentalization, we propose to track capabilities in types, and Gradient concretely uses capture tracking for this purpose, which is another recent system, and it's the capability equivalent of an effect system. So let's just focus on how can we use that to enforce some security policies. So in this slide, we have a capture-checked version of log4j. The hash is no longer there, so this is a less dangerous variant, and that's because we can statically restrict access to devices with ascriptions. Okay, so this particular main can only access the file system device, but not the network, nor any other device, right? And that's because of the capture annotation that it has, the one after a hat, right? That's like a return type ascription, but for what capabilities can be mentioned by the body of the method, and not the value returned from the method. Okay, so if we wrote this code, we would get a compiler error because log4j accesses too much. Okay. So let's assume that we continue with some nice4j package, which makes the compiler happy because it only accesses the file system. So what we also propose are restricted blocks, which use types to statically check that only certain capabilities are accessed. This is basically the same sort of ascription. It's only on a block and not on a method. So the code in this particular restricted block can only access log, and that's a way to express that this code can at most do logging, and it cannot access any other system feature, right? And it piggybacks on object capabilities. So to wrap this up, we can use these capture ascriptions to create static compartments for capture-checked code, and these work both for classical code and for object capability-based code. Okay, so let's briefly go back to log4j with the danger hash. So what that meant is that this package is not capture checked. So we want to run such code under an enclosed block, and what happens if we forget one? Well, we get a compiler error. And that works because here, now the type system tracks that all definitions in log4j are capture unchecked, right? So that's our equivalent of being dynamically typed. And we forbid main concretely from accessing capture unchecked code, either directly or indirectly, right? So this is a violation of that. Okay, and to wrap this up, if we added an enclosed block, we basically assert what devices may be accessed during this block, right? So that's our equivalent of a dynamic type check, but on access to capabilities. Okay, so the last recap is that tracking capabilities in types allows statically enforcing the POLA on packages of classical code, and that code does need to be capture checked, but that's much easier than a full migration to object capabilities. Okay, so we saw that what gradual compartmentalization and gradient are about. Let's finally talk about our other results. So we develop the formal foundations for the approach. That's the other major contribution. We take the core capture calculus and we extend it with quite a number of features necessary to support gradient. So we add mutability, we add modules, we add object foundations, and on top of that, we also propose this gradual capture tracking idea. And we prove that the resulting system is sound. Okay, so also a few words about how we validated our approach. I promised that capture checking a package is not too much work. That's why we chose capture tracking, because it was designed to require less annotations than an effect system. And to validate that, we migrated an existing Scala library. And the result of that is that no major refactoring was necessary. And most of the lines that needed updating were very trivial. And in general, few lines had to be changed. Other than that, we also provide a detailed description of how gradient can be implemented based on existing literature, and we evaluate the performance of an enclosure-based implementation. Okay, good. Thank you for your attention.
Do we have questions for Alex? James?
Thank you for a great talk and some obviously really interesting work. I've actually got two questions. The first one is when you talk, and I'm still somewhat confused, I'm jet lagged more than usual today. You said things were like dynamic checks. Did you mean that they were dynamic checks? So when you're encapsulating the classical code, because you're talking about a performance overhead there.
Yeah, I mean, so right here, we would have a dynamic check, right? So that's basically what I was saying.
Does not have a dynamic check.
Okay, sorry. No, I won't scroll back over there. But basically, over here, this body of main can only perform file system related syscalls, right? So that's a dynamic check.
Right, so effectively what you're doing is injecting the object capability for the file system into what Mark Miller would call the sort of ambient authority. So now
it's like a reverse dependency, right? But yeah, you could view it as saying that within this block we have at most this amount of ambient authority.
Well, within this block we can get access to FS even if we haven't been passed it.
Basically, yes, but only FS.
Right. I shouldn't say implicit. The other question I was going to ask is, how do you think this relates to the sort of effect handler stuff that's going into OCaml and the functional people seem to love? And if you just sigh, that'll probably do. Okay,
do you want a particular part of an answer to that question, or?
Well, ideally, I'd want one sentence that says something like, I don't know, object capabilities are effect handlers done without control flow inversion, but I don't know.
Yeah, that's what you could do. So, I think that something like this form of gradual typing should also be possible there, right? And similar sort of enforcement should be possible. And so basically, you can view handlers like they are objects passed around, right? It's
right.
Sorry, I'm maybe moving a bit too fast.
Right. Okay. I mean, we should probably take it offline, but
yeah, it would be great to chat about that.
All right. Let's thank Alex again.